Okay, class, this is part two, second order systems. And this part two, we're going to talk about behavior. Okay, behavior. So as a reminder, this is the transfer function for a second order system, omega n squared over s squared plus 2. And then this is actually the Greek letter zeta, but I'm using z because I can't write zeta. Zeta omega n s plus omega n squared. Okay, so this is what's called the standard form. Okay, the non-standard form was h of s equals b over s squared plus as plus b, but you see it has the same structure. Okay, b is omega squared and a is 2 zeta omega n. Okay, so the nice thing about this are these constants have physical or they have useful interpretations. So this one here, omega n, is the natural frequency. Okay, frequency. And the zeta is the damping factor. Okay, damping factor, zeta. Okay, zeta, that's zeta, damping factor. And those two values determine the behavior of the system. And the kind of behavior we're going to look at is what happens if I have a second order system and I subject it to a unit step input. Okay, so I have a second order system and I apply a unit step input to it, right? And I'll see what happens. Okay, right, because it moves to a new steady state. All right. Now, how do we look at the behavior of this? Well, the way to look at the behavior is to look at the characteristic equation. And the characteristic equation, of course, is the denominator. So it's 2 zeta omega n s plus omega n squared equals 0. And the idea is we have to find the roots s, right? The roots. This has got two roots, of course, quadratic. What are the two roots of this? And those roots will determine the behavior. Okay, so those roots, we also known as the poles, of course. Okay, so the roots are pretty straightforward to evaluate. Minus zeta plus square root zeta squared minus 1, and the whole thing is multiplied by omega n. Now the other one, the other two, the root, of course, is just the conjugate of this, so it's minus zeta minus, not plus, square root zeta squared minus 1, close brackets, multiplied by omega n. You'll notice that the poles are scaled basically by the natural frequency. Now, the values that S1 and S2 can take are heavily influenced by obviously zeta, and in particular, the value inside the root can be negative or positive, all right, depending on the magnitude of zeta. So if zeta is greater than 1, so let's just put it on here. If zeta is greater than 1, then we end up with real numbers, right? Real numbers. If zeta is less than 1, we end up with complex numbers, okay? If zeta is 1, we end up with with just an imaginary number, right? No real part. Okay, so those are the sort of situations we can get from the poles, and actually these three situations here, and there's one other actually, zeta equals 1. So when zeta equals 1, we also have real, but now the two roots equal each other. Okay, now in all cases, the real parts are negative, right? The real parts are negative. Okay, I guess except perhaps, I guess, for this case, when the real parts are 0, but the real parts never move into the positive quadrant. Okay, they're always on the left-hand plane, right? So they're always negative. So these systems are always stable, except maybe for this one, which one could class as marginally stable, which we'll come back to in a minute. All right. Now you've seen these patterns of poles when we talked about eigenvalues and the behavior of 2D systems in terms of eigenvalues. You know, you had stable nodes, stable spirals, unstable spirals, and you had center. Well, a number of those correspond to these ones here, okay? We don't have any unstable spirals or any unstable nodes, but we do have stable nodes and stable spirals and the center. Okay. All right. So let's have a look at these cases then, one by one. So I'll draw a table here. So that's going to be the case. That's going to be the value of zeta, and that's going to be the roots, and this is going to be the behavior. Okay, it's going to be the behavior. So case number one. Case number one, we'll consider the easy one is when zeta is greater than 1. Okay, greater than 1. I'm going to draw on this side, I'm going to draw a graph showing you what that might look like. Okay, so zeta equals 1. The two roots, again, they're negative. Okay, they're real and negative. Okay, and the behavior, there's a technical name for this, is called overdamped. It's called overdamped because this behavior is quite sluggish. It's not oscillatory in any way, it's monotonic. And if I were to draw it on this graph, it would look like, let's say the steady state is here. I put a step input at this point. So the new steady state is up there. And I apply a step input, I'll get something like that. Fairly slow, and slowly approaching the new steady state, okay? So this is going to be case 1, okay? Now for case 2, so if we start off with a high Z and we slowly decrease Z, or zeta, sorry, we eventually reach zeta equals 1, okay? So we eventually reach this, not that one, this situation here, okay? Again, they're real, the same color, they're real, but this time S1 equals S2, and they're still negative. Okay, they're negative. Okay. All right. So remember, if Z1 is if Z is 1, this whole root disappears. We're just left with Z. Okay, and it's the same Z for each pole, but scaled, of course, by the natural frequency. In this case, it's called, the technical term for this is critically damped. And in this case, this is the fastest behavior you'll see. So it's fast. And if I were to draw critically damped one, it would be something like, pretty fast, right? Much faster. All right. So this one is going to be case 2. Okay. So it's pretty fast. The next one we're going to look at is case 3. And case 3 is where zeta is less than 1, but it's greater than 0. Okay, it's not at 0, it's greater than 0, but less than 1. In this case, S1 and S2 are complex. Okay, complex. The real parts are still negative, though. So the real parts are still negative. Okay, so it's stable. The technical term for this one is underdamped. Okay, underdamped. And the minute you see complex poles, you immediately must start thinking of sinusoidal behavior. In this case, it's damped oscillations. And they're damped because the real parts are negative. So if I were to draw, let's say a different color again, if I were to draw this one on this curve here, I'd see something like that, okay? And so this would be case 3, all right? So you start to get oscillations, right? And in fact, the smaller, the closer you get Z to 0, the more crazy the oscillations become. In fact, in case 4, when zeta does equal 0, real parts are 0, and you're only left with an imaginary part, okay? 2 conjugates. And the technical term for this one is undamped. So this is the equivalent of center, which we saw when we were looking at the eigenvalue behavior. And this one here, I'll draw a separate plot here for this one. This one is just, it's basically sustained oscillations, okay? But not very interesting for us because these aren't what are called dissipative systems. These are sort of frictionless systems that don't lose energy and they just keep on swinging forever. In the real system, there'd be friction, of course, and these things would slowly slow down. But anyway, that's the idealized situation for case 4. Now you can also look at these, of course, in terms of the pole plot, right? So the poles plot, or technically pole 0 plot. I'm just going to plot the poles. So what color? So for red was that one. So the red poles were real, no imaginary component, and they were different. Okay, so that was number 1. Number 2, which was when zeta equals 1, they're both real again and negative, but this time, what was the color? Blue. But this time they're sitting on top of each other. Okay, sitting on top of each other. The next one, which was the underdamped or the damped oscillations, both complex terms, and that was purple. So that means they're, somewhere like this. Okay, 2 conjugates. And then finally, I had green, which was for the center or the undamped. These were purely imaginary poles. Okay, so that's another way of looking at it. Notice they're all on the left-hand side. There's nothing on the right-hand side at all. All right, so that's basically it, actually. That's basically it, right? So you have, for zeta, a high zeta, right, above 1, you get this a slow response, okay, sluggish. Zeta approaches 1, the response gets faster and faster until you reach the limit when zeta is 1, when we claim it's fast, otherwise known as critically damped. After that, it's so fast that it starts to overshoot. And that's when you start getting the purple line, which are the damped oscillations, when zeta is below 1 but greater than 0. And finally, when you're at zeta is 1, you get free-flowing oscillations that don't stop. Okay, thanks.